되셨나요?
예.
네, 알겠습니다. Hi everyone, welcome to APCTP String Seminar. Let me introduce today's speaker, Professor Chanju Kim from Ewha Women's University. Today, he will talk about supersymmetric inhomogeneous field theories in 1+1 dimensions. Please join me in welcoming our speaker, Professor Chanju Kim.
Thank you. This talk is based on my recent work in collaboration with Dr. Bogomolny and Professor Nonvacuum, which will soon appear in JF. As you know very well, supersymmetric field theory is usually studied as an extension of Poincare symmetry. And in the case, they have very nice properties, such as energy is positive semi-definite. And if supersymmetry is unbroken, then vacuum energy is necessarily zero. Otherwise, vacuum energy is positive if supersymmetry is broken. And also there are VPS objects which preserve part of supersymmetries, and they satisfy the first order Bogomolny, so-called Bogomolny equation, which minimize the energy for a given topological sector. And but actually, there are many typos. Sorry, supersymmetry can exist in theories where Poincare symmetry or translation symmetry is not relevant or is partially broken. For example, in non-negative field theory, there are also supersymmetry. There can be a supersymmetry, and also, for example, the theory can have explicit coordinate dependence in the action with the supersymmetry. So, for example, so-called genus Yang-Mills theory can be generalized to have supersymmetry, and also in 3 dimensions, there are ABJEM theory deformed by inhomogeneous mass. And also, one can consider supersymmetry with impurities. And also in 2 dimensions, for example, there are theories with supersymmetry, which has boundary or which has defect. So there are actually many examples of supersymmetry without Poincare symmetry. And in that case, we can ask the following questions. So, as I said, energy is positive semi-definite in usual theory with Poincare symmetry, but is it true even in this case? Well, naively, one can say yes, because there are still supersymmetry in other directions. For example, in 3-dimensional space, if the translation symmetry is broken in z direction, but then there are x and y directions which where Poincare symmetry is still symmetry. But in that case, then one may think that Hamiltonian is somehow scarce of the unbroken supercharges, then the energy may be still positive semi-definite. But it turns out that this is not true, as I showed.
Here, when you say it's broken, does it mean it's explicit broken or spontaneous broken? Explicit broken. Okay, yes. Thank you.
So in this talk, I will consider the simplest supersymmetry in 1+1 dimensions, and I will restrict myself to only classical case. So we consider one real scalar multiplet, which consists of one real scalar and one Majorana fermion. So in the case, the number of supercharges is 2. And this is the usual Poincare invariant series, where the potential can be written in terms of square of the superpotential. And this is the supersymmetric transformation. And these are 2 supercharges. And supersymmetry is superalgebra is simply given in this way, where T is the central charge, which actually is the difference of superpotential at special infinities. Then this can be written and in this way. The energy, which is P0, can be written as square of supercharges plus minus the central charge. And we have, because we have two supersymmetries, actually this is, this bound can be written in two different ways. One bound is that E is larger than minus T, and the other bound is that E is larger than plus T. So that means E is larger than the absolute value of T. So this is why the energy should be necessarily positive definite. And for the constant configurations, because this topological central charge is just a difference between two superpotential. If these are constant, then this is automatically 0. So usually one does not consider this central charge when considering, for example, vacuum configuration. And the vacuum energy is 0, of course.
So this is n equal 1 case, right?
Yes.
This center, usually n equal 1, do we have, so this is kind of kink or like a soliton, like object when there is non-zero central charge? Or?
That's right. That's right. So
okay.
Usually we do not consider this the central charge.
N equal 1 case. So yeah, I see.
But now, suppose we give an explicit coordinate dependence to the superpotential in like this. In this case, supersymmetry is explicitly broken. But actually, this one of two supersymmetries can be saved by adding a term in the Lagrangian, which is just a special derivative of the superpotential. Then this theory is invariant under the same supersymmetry, but now with the condition of the superparameter. So there is only one supersymmetry. From now on, I will choose the upper sign. So in this case, I mean, we have the potential is these two terms, consists of these two terms. So we have also explicit coordinate dependence in the superpotential, like this. In this case, energy can be written in this way. Now we have only one supersymmetry, so the energy is bounded by T only, plus T only, not by minus T. And the central charge is actually is given by the same expression, but now with the explicit partial derivative with respect to x. And this can also be seen from the positive part of the energy by rewriting this energy in terms of a complete square plus central charge. And this vanishes if this vanishes, and this actually is called the Bogomolny equation, which is simply given by this. And if this is satisfied, then the second order equation of motion is automatically satisfied. One can explicitly check that this is satisfied always.
So here, the energy is conserved, but the momentum is not conserved.
That's right. Momentum is not conserved.
So such corresponding supercharge is also broken, and
right.
Yeah. So what happened to this broken charge? So is it just
well,
like you can write down the expression? I mean, I just wonder, like this, you have a charge, and there would be some other previous charge, but is it just a meaningless quantity, or does it have some physical meaning after broken? Or
well, I mean, in usual mechanics, I mean, if there is a potential, you can think of momentum, but the momentum is not conserved.
Okay, that's or there is no further physical meaning.
I don't know.
you cannot. Yeah, probably you cannot define the momentum of it. Yeah, yeah, that's true. Yeah, okay. Thank you.
And now let's solve this Bogomolny equation. Well, in ordinary homogeneous theories, the Bogomolny equation is trivially satisfied by constant configurations. I mean, if phi is constant, then the solution is just the extremum point of this superpotential. So these are all solutions of the homogeneous series. In this case, as I said, the central charge is 0, then vacuum energy is also 0, trivially. But now we have explicit coordinate dependence in the superpotential. So there's no reason that the solution of this equation is constant. And especially, there is no reason that the vacuum is a constant configuration. And also, as I said, energy is bounded, only bounded by T, not by absolute value of T. And the central charge is the difference between these two values. And as I said, for the vacuum, even for the vacuum, the configuration is not constant. In that case, T may not be zero, may not vanish. In particular, T can be negative. So there is no reason that energy should be positive. So these are two differences in inhomogeneous case, and I show that these actually these features are realized in a series I consider.
Solution of this.
I got a question
Yes.
about which supersymmetries surviving. I mean, among two original supersymmetries.
Right. So
that depend upon the sign of added term.
That's right. There can be two signs, and depending on the sign, we have to impose two different conditions. So one is conserved and the other is broken.
I see. So minus sign, if minus sign is added there, then plus supercharge will be surviving.
Yes.
Oh, okay.
Right. And another interesting feature of the inhomogeneous theory is that there can be, other solutions which are not vacuum. So in this case, unbroken supercharge is 0, and energy is just given by the central charge. And because this Bogomolny equation is first order, and the solution is in general not constant, then in general, the solution has an integration constant. But the boundary values of the field at special infinities are discrete because they are extrema of the superpotential. So in this case, the central charge is also discrete. Possible central charges are discrete. But energy, so the energy cannot depend on this integration constant because this integration constant is continuous. So that means that energy is independent of C. So variation of C should be a zero mode of the system. So in this inhomogeneous series, existence of a zero mode is a kind of generic feature of the system. And interestingly, I mean, the translation symmetry is broken, but this is kind of zero mode representing the position of the solution, such as kinks. And actually, this can also be generalized to contain non-trivial kinetic terms like this. In the case, we can trivially modify these terms like this. Then this is also invariant under this Specimen Transformation.
Can you explain this zero mode existence of zero mode intuitively?
Well, I'll show you explicit examples later.
Oh, okay.
And also, the corresponding Bogomolny equation can be written in this way. But in this talk, I will not further consider these non-trivial kinetic terms. And actually, after I finishing this work, I got an email from this guy, and he said that they have already considered many parts of our papers, and their formulation is like this. Their basic motivation is to introduce impurities to the system, and somehow they started from the simple examples, and they eventually obtained this Lagrangian. But this is actually equivalent to our formulation once we identify our superpotential like this, up to a total derivative. But this Lagrangian is kind of non-standard in the sense that this Lagrangian has a linear term in the derivative of the field. So in the homogeneous limit, this does not go to the usual Lagrangian, and this does not reproduce the standard energy expression. But other than that, their formulation is identical to ours. So as far as the equation motion is concerned, they have the same Bogomolny equation, but the energy of their energy is different from ours. And I have also a remark on the energy. Actually, the energy in the inhomogeneous theory has no absolute meaning, just as in usual non-supersymmetric theories, because you can always add a field independent term like this. Then this does not have any effect on the supersymmetry, and the energy is shifted by this amount. Now this gives some constant shift because these two values can be different, but other than that, there's no physical effect. So in this sense, negative energy is not kind of absolute, does not have absolute meaning. And actually, so I would like to fix this ambiguity by requiring that every term in W depends non-trivially on phi. So this partially fixes this the ambiguity, although there can be some other ambiguities. But in many cases, this can provide a natural choice for the energy.
So here, this kind of trick is possible because you don't expect this translational symmetry. So that's why this like a trick is possible. So in usual translational invariance theory, you cannot using this argument.
That's right. But okay. Even in translational invariance theory, there are, I mean, in some sense, ambiguities because like this term, you can add this kind of term linear in the derivative of field. In that case, energy becomes different. But nobody think about this kind of possibility in homogeneous theory. So I just neglect this kind of possibilities. Although these guys prefer to this term, this form. This kind of ambiguity exists even in translation invariance theories.
So you mean usual Suji theory, like energy is positive definitely also has some ambiguity.
That's right.
like
That's right.
Oh, I see.
Up to this ambiguity.
Okay.
So, I mean, there are infinitely many different kinds of inhomogeneities. So I'd like to consider two simple cases. One is just overall rescaling of the superpotential. So given a superpotential W is 0, I'd like to multiply Gx and define this W phi x as my new superpotential. So in this sense, this can be applied to any existing supersymmetric theories. So in this case, the corresponding deformed potential is written in this way. This is the usual square term, and this is the derivative of the superpotential. And the corresponding Bogomolny equation is given in this way, where this is simply the derivative of W with respect to phi. Then actually this Bogomolny equation is always solvable because this Gx can be observed into the redefinition of the coordinates in this way. So if we transform this coordinate into a large Gx like this, then the derivative of this can observe this term. So that means there's no explicit coordinate dependence, and one can already solve this equation because this is just first order equation. Now, because energy depends on the asymptotic values of the superpotential, let phi I be the extreme point of the W0. Then this constant configuration, I mean, which are the extreme points of this W0 are always solutions because, I mean, if this is constant, then this vanishes and this vanishes. And this is already observed into the coordinate. So they are always solutions. And the energy of the constant solutions are simply the central charge. And in this case, the central charge is the difference between the two potential values. But now there are inhomogeneous parameters multiplied. So the energy is given by this. So that's the difference between the two asymptotic values of the inhomogeneous function. And the vacuum energy would be the minimum of these values. But actually, there are other solutions. Now, that to be explicit, we from now on we consider explicit theories. So, as an example, let's consider sine-Gordon model, supersymmetric sine-Gordon model. So, in this case, the sine-Gordon theory, I mean, usually has potential of this form, where the mass parameter is multiplied in front of the sine potential. So now we can identify this mx as our gx here, like this. Then all these equations can be immediately applied. And so if we make this mass inhomogeneous, then we have this additional term. And this undeformed superpotential has extrema at these values. And the Bogomolny equation is given this way. As I said, for these extrema, because they are solutions, and the energy is given by this form, which is nothing but this one, the difference times the value of the superpotential at that point. So they are the extrema times the value of the superpotential at that point. And the vacuum energy is the minimum of these. So that's the minus absolute value of this. So as you see, this is always negative unless the two asymptotic values are the same. And also because there is a plus minus signs here, the degeneracy in user sine-Gordon model, the degenerate is lifted to twofold. So the vacuum configuration is like this, where the delta is given like this theta function, and the other half configuration have positive energy, which is absolute value of the vacuum energy, because this is like this. And there are, of course, kinks, for example, kink solutions in user sine-Gordon model. So we can also have such kind of solutions in this case. And that can be also be obtained, as I said, because this is already solvable by introducing this new coordinate, for example, new kind of coordinate. Then the general solution of the Bogomolny equation can be given is given in this way. So this is the solution, general solution of this equation. So which is given by arctangent of something, and depending on the asymptotic value of this exponential mu, the phi goes to either 0 or other values. And the energy of the solution is always energy of this solution is always positive unless the C is 0, where C is the integration constant, as I said. So the energy is given actually by this, can be written in this form. So there are absolute values of this. And as I said, of course, this is independent of the integration constant. So C is 0 mode.
So this inhomogeneous sine-Gordon, is it also integrable model, or?
I don't think so. I mean, because M is, arbitrary parameter function. So maybe, in sharp interface limit, if the M is given by step function, for example, in the case, this may be integrable, but I did not check.
Okay.
And it turns out that depending on the sign of these two asymptotic values of the mass, the nature of the solutions change very drastically. So if the mass is positive, then the solution goes to asymptotically to these values. So let's just see this figure. So especially minus infinity, they all goes to 0. But positive infinity, the phi goes to either 2 pi or minus 2 pi. Where I put beta equal to 1. And this is for ML equal to 2 and MR equal to 1. So you can see that this is kind of kink, but you can see that the slope of this kink is steeper here, where because the mass is larger than the right side, and here this goes to rather slowly because the mass is just less than the left side. And as you see here, by the way, this solution is obtained with this kind of mass function, hyperbolic tangent basically, but now with constant. And actually the intermediate shape of the solution can be very different. If we choose very complicated MX, this is just for hyperbolic tangent. And if we choose the other function, then this can be very complicated, for example, like this. But this is just a simple example.
So here it's a stationary kink.
Right, this is stationary. And
do you also have some non-stationary kink? Like
maybe, but I didn't think about it.
Okay.
Because I mean they are not supersymmetric solutions of the Bogomolny equation.
This is just.
Here I just consider Bogomolny equation, which is always static.
I see. Okay.
And all these solutions are degenerate, and of course, here the integration constant C represents the position of this kink or anti-kink solutions, where C appears here. And because of the inhomogeneous term, actually, because this term, as I said, the degeneracy of the vacuum are lifted. So here the periodicity of the theory is not 2 pi but 4 pi now. So for example, this solution and this solution are not cannot be identified. So in this sense, I mean, we have two kinds of kinks and two kinds of anti-kinks. Of those solutions, I mean, if in usual homogeneous series, there are kink solutions and anti-kink solutions. So if, for example, they are all supersymmetric. And so, for example, we have this kind of kink solution, but there can be also this kind of anti-kink solution. Also, here we can have this kind of kink solution in usual homogeneous series, but those are now no longer supersymmetric in our inhomogeneous series, so they do not appear in this solution. So in this sense, I mean, the half of the solution are not supersymmetric in this series. So only these solutions are supersymmetric. And this solution, these kink and anti-kink solutions, I mean, we can interpret this as kink and anti-kink solutions, but these solutions are for the case that the mass parameters, both of the mass parameters are positive. But if one is negative and the other is positive, then we obtain completely different type of solutions. In that case, the asymptotic value of the field goes to either, goes to the same value, either 2 pi or 0, like this, or minus 2 pi in this way. So if the solution starts from the 2 pi, then it should end at 2 pi. So in this case, we have this kind of solutions, and you can interpret this as a kind of kink anti-kink pair. And in usual sine-Gordon theory, we have this is called usually breather solution, which is a kink anti-kink bound state. And in usual theory, these solutions are not static; they are time dependent. But in this inhomogeneous series, these solutions are all static. So that's the difference. And more interestingly, these solutions, all these solutions have the same energy. They are all degenerate, and they actually can be continuously deformable to the constant solution. And this integration constant C represents all these solutions. So by varying C, you can obtain all these kind of solutions. So these are actually one parameter family of solutions. And below this, actually, I just drew only this part, but below here, you can have also the half of the solution like this. So all these solutions form one parameter family of degenerate solutions. And this constant solution is just a special case of this one parameter family of solutions. And there is another constant solution, which is of course a vacuum. So this one-parameter family of solutions exists around this constant solution, which is not vacuum. So there are two, as I said, there are two constant solutions, two types of constant solutions. One vacuum, the other higher energy. And around this constant solution with higher energy, there are this one-parameter family of degenerate solutions. And by varying C, this can be deformed deformed in this way. So even if there is no translation invariance, there is still zero mode of this kind. And in this case, C does not represent position of the kink or anti-kink. This represents if you interpret this as in kink anti-kink pair, then this C represents the distance between kink and anti-kinks. And so we have three different type of solutions, and the energy are given in this way. This is the vacuum, which is negative, and there is other constant solutions which are not vacuum, and the energy is the absolute value of this vacuum, as I said. And we have a non-constant solution, which are either kink or anti-kink or kink anti-kink pairs, depending on the sign of the mass parameter. But you can easily see that if you choose, depending on the sign, this M1 and E1 and E and C, these two energies can be the same actually. If one of these is negative, then this should be the same as this one. So that means that E1 is E and C. In other words, if both the parameters have the same sign, we have three different energy levels. One is vacuum, the other is this one, and the other is this one. So this solution has the highest energy. But if the signs of the masses are different asymptotically, then you have only two discrete energy levels. And this is actually consistent with what I said in this page, where this non-vacuum constant solution and these solutions are all degenerate. That's why, they have the same energy. And as you see, this kind of feature, the one-parameter family of degenerate solutions around the non-vacuum constant solutions is kind of a generic feature of this inhomogeneous theory. And also one can consider a periodic mass function, for example, like this. Then the solution is like this. So this kind of mass function is relevant for compactified series on a circle. In this case, because this is periodic, there's no longer difference between this constant solution and this constant solution, and they all have the same energy. And also, these solutions are all can be deformed to other solutions. So that means that the potential has a discrete minima at 2 pi n, but actually they there's a flat direction in the solution space which connect this solution and this configuration, this configuration. They are all connected by these solutions with the same energy. So it's kind of interesting situation here. So all the minima of the potential can be continuously connected by integration constant. And now we consider another type of inhomogeneity. So let's consider this kind of superpotential. Then it will give a potential of this form. This is 5 to the 6th theory because there is a square.
I got a question.
Yes.
I mean, for this kink anti-kink solution, where the parameter C is, I mean, interpreted as more site.
Right. You can
The
interpret
solution.
right.
I mean, presumably the solution should be localized, right?
Well, I mean, you can separate this kink and anti-kink part as you want.
So that is the size.
Right. You can interpret this as a size, and the size can be very different from 0 to infinity.
Okay. I see.
So with this superpotential, you obtain the 6th order potential, and where W is the usually scale of the vacuum expectation value because it appears here. But now we consider this as a position-dependent function. If we make this coupling constant lambda position-dependent, then we will go back to the previous case. But now we keep this lambda constant, and instead we vary this vacuum expectation value. In the case, the derivative of W with respect to X gives this term. And here, interesting thing is that this W vacuum expectation value would be vacuum expectation value may not be positive. In that case, I mean the minimum of the potential, even the number of the minimum of the potential can change. So, for example, with the Wx as a hyperbolic tangent, then if W in the the positive X region, we have 3 minima, but for negative X, we have only 1 minimum. So, for example, like this. Here, this is positive X, this is negative X. And in the positive X, we have 1, 2, 3 minima. And in the negative X, we have only 1 minimum. So this potential kind of smoothly connect two regions while keeping the supersymmetry. So you may think of this as a kind of two heterogeneous systems joined together. For example, part of the system you apply, for example, external field, and the other half of the system you don't apply the external field, and those kind of situations. Then the Bogomolny equation can be written in this way, where W appears here explicitly. And actually, very fortunately, this solution is completely solvable explicitly. And of course, the energy also will depend on the asymptotic value of the superpotential. So let's just call WL and WR. W and WR as the asymptotic values of this W function. Then, depending on the sign of this W and WR, we have, as I said, different values of asymptotic, different possible values of phi asymptotically. And but there is always a constant solution. Obvious solution is constant solution because if you put this 0 and 0, then this is trivially satisfied because this phi x is multiplied here. Or in picture, you can see that these are flat. This is a flat direction, so always constant solution exists at the origin. But there are other solutions. And as I said, this is integrable explicitly. And the solution is given this way. where omega and c are defined in this way. And from the, in this equation, we have also this integration constant c. And depending on c, we have different. You can have different values of different asymptotic values of phi. And this is rather technical. So I just skip this part. And I show only the result. If the WL is positive and if C is larger than the c at infinity, where c is defined like this, but I'll just mention that this is just some condition for integration constant. In this case, the asymptotic values of the field can be identified this way, and accordingly, the energy can be calculated in this way. And as I said, energy, there's no reason that energy should be positive. So actually, there are two cases that energy is negative, can be negative. And these are non-constant solutions. And as I said, there is always a constant solution, trivial solution with vanishing energy. So comparing these energies, we see that this constant solution is not always vacuum, because there can be negative energies, which are not constant solutions. So the true vacuum is this configuration. And
how does this solution look like?
Yeah, I'll show you.
Okay.
So because this is a general solution for arbitrary Wx, this is too general, so I restrict the solution with this hyperbolic tangent type Wx. Then in this case, the general solution can be expressed in terms of a hypergeometric function, but still this is complicated. So I'll just choose some simple Wn and Wr. So the simplest case is WL equals WR. In that case, this is just a constant because this vanishes. So this is the usual homogeneous case. In that case, we have kink or anti-kink solutions. And if WL is equal to 2 times WR, then the vacuum expectation values are square root of this. So this goes to WL, this square root of WL, this goes to square root of WR. And there is also corresponding solutions in the negative region, but we can forget this because this is G2 symmetry. So this goes to WL, which is 2 times W, square root 2 times the square root of WR. So starting from here, it goes down and goes to WR. So this is this looks like an anti-kink solution. And there are 2 types of solutions. One goes to the WR and the other goes to 0. In this case, the vacuum solution is just constant solution because here this is larger than this one. So in this case, this has positive energy. So in this case, the vacuum is just constant solution, and there are other type of solutions which looks like a kink or double kink, like this or like this. If WL is equal to half of the WR, then the asymptotic value goes down here. The solution looks like this. In this case, this solution has negative energy because this is smaller than WR. So in this case, vacuum is no longer this phi equals 0, but this is the vacuum, or this is the vacuum. And there's also a solution goes to 0 at special infinities. And another possibility is that WL equal to 0. So in that case, at negative infinity, the field vanishes, but now it vanishes logarithmically, so very slowly. Even in this case, also the solution vacuum is not constant, so these are vacuum. And as I said, this is constant solution, and these all have the same energy. When actually the energy is 0, so these form a one-parameter family of degenerate solutions around this constant solution, which is not vacuum. This is the same phenomena as is so in the sine-Gordon case. And this is a solution of the theory where potential in the left side the potential is pure 5 to 6, and the right side the potential has three degenerate minima. Finally, if we choose pure hyperbolic tangent as a W, so WL is equal to minus WR, then we have a similar solution, but now exponentially decaying solution in the negative X region. So this is also, here also this is vacuum, which has negative energy, and we have also constant solution with vanishing energy, and also all these solutions have vanishing energy. So these all form one parameter family of constants, one parameter family of solutions with vanishing energy. Right. So let me conclude. So here we consider the inhomogeneous series, but here supersymmetry. As if seen, the energy can be negative, even if the theory has unbroken supersymmetry. And the vacuum may not be constant, which can have arbitrary complicated type of configuration. And also we have a zero mode. We see that zero mode exists around the non-vacuum solutions for any inhomogeneity, even if the translation symmetry is broken. And the physical interpretation of the zero mode is sometimes position, or sometimes a separation distance, or sometimes the size of the solution, and so on. So it may be interesting to study the zero mode dynamics and also higher order excitations. So in this sense, compared with the usual homogeneous series, we have much richer structure of solution space. Here I consider only two types of inhomogeneities, and one can obviously consider other type of inhomogeneities. For example, you can vary both coupling constant and vacuum expectation values simultaneously. Or even you can add any arbitrary term into the potential. That may represent two or more heterogeneous systems joined together. This kind of thing may be interesting in condensed matter applications. Here I consider only 1+1 dimensions, but you can think of similar things in higher dimensions or more field content. Yeah, I'll stop here. Thank you.
Thank you very much for the very great talk. Please ask a question.
I got just one question. Or I mean, somehow can we define energy momentum tensor for this theory?
Yes, implicitly we can define energy momentum tensor, and but
it will not be symmetric.
But the energy momentum tensor is not conserved. mean,
it's
the momentum
it's-
is not conserved. So, for example, if you consider d mu t mu nu, then the special part is not zero because it has an explicit force.
I see. So okay. So there is some kind of external force.
That's right.
In some sense.
Right.
I see. That is the magic. Okay. Thanks.
Actually,
Well,
if you
I
calculate
mean,
the pressure that, yes,
coupling to the gravity, I'm not so sure.
yeah, I didn't think about it. And actually, I secretly calculated the energy in Janus-Yang-Mills theory, actually. And it seems that there is also some cases that the energy can be negative. I don't know the physical meaning, but when
You
I
mean to the Yang-Mills?
no 4D.
4D.
Yeah, well, I mean, for the I computed. Well, I mean, I also computed, you know, the energy density, for instance. I mean, for the multi-genus solution. And what I find is, you know, it violates average null energy condition. And well, then I don't, well, I mean, normally we believe that average null energy condition should be, in any case, should be respected. But well, certainly, you know, some translational invariance is broken, and so we don't have a full Minkowski, you know, Poincare symmetries, and so the strict proof is well, since strict proof is done only for the Poincare invariant case. And so, well, I'm not so sure what we can say. That is one comment.
Okay.
Yeah, energy can be negative there, which seems to me, I mean, problematic. Yeah, but there could be some external element.
Right.
Yeah, there could be some external, to make the configuration, we need something external. Well, so that external part may not be considered, which should be positive, should carry positive energy. And so I'm not so sure we can be that precise.
And here you are focused on this energy. So maybe you are not that interested in this case, but what about you add the time explicitly instead of the x? Is there some new feature, or is it just parallel to this calculation?
Maybe, I don't know. I didn't think about it.
I see. Because if you add in t, then energy is meaningless. So
Right.
I don't know what to say, but and also I have a question, but because you already mentioned that you only consider the classical, so maybe you would say you don't know, but I would like to ask, what about this Bojonization? Is it some possibility of this Bojonization in this case?
I really don't know. Maybe, I mean, in some limit, like a step function limit, that may have meaning, but yeah.
So I see. So I just wonder, like, usually there is an isolation between the sine-Gordon and
Right.
this fermions. So,
Right.
or in usual 2D theory, you can bosonize, but here, because you break the string relation, so I just wonder whether there is also this analogous description in the fermionic theory. So,
Right.
So probably this kind of kink would be related to the this fermion. Usually, if that
Yes,
is sine-Gordon, so
yes.
here fermion is just should be stationary in somehow, but I don't know. Yeah.
Excuse me.
Yes.
Can you hear me?
Yes.
Yes. Thank you very much for your presentation. I have a question about the last part of the discussion about the higher dimension, in which you mentioned that, well, you mentioned at the end some topic about that. I would like to ask you about this last part. I don't know if the equation, the solution, can be treated similar to quantum field theory, in which they use something called the dimensional regularization, in which they assume that have 4-dimension and arbitrary using some technique. They try to evaluate some solution by the amplitude. Well, in higher dimension, I am not sure if using a similar technique, there is a possibility to study the solution using dimensional regularizations by higher, or maybe, well, using maybe 4 or more dimensions by the solutions. I'm not sure if my question is clear.
I'm not sure whether I understand your question.
Yes. Let me check. No, look,
I mean, this
look.
is just a pure classical consideration as far as this talk is
Yes.
concerned. So, I mean, there's no room for regularization or.
Yes.
I didn't
Sorry.
expect any.
Maybe I reformulate bad the question. So my question is technical. You have a equation in which you have some solution, and you propose to extend or increase or try to control the number of dimensions. I imagine with that some technique that that is used in quantum field theory with the dimension regularized by Feynman diagrams. So I would like to know if that can be similar to describe or try to evaluate some extension by the solution of your problems.
Okay, I mean, you can consider this 1+1 dimensional theory as a dimensional reduction of some higher dimensional theories.
Yes.
Or, for example, this kink solution can be considered as a kind of domainal, for example, in 3+1 dimensions. In this case, the solution of this I described is just a domainal solution in 3+1 dimension.
Mm-hmm.
So yeah, in this sense, this solution can be embedded into higher dimensions.
Okay. Okay. And what happened? I'm sorry for interrupt you again, but what happened if you try to trick this problem, but in, well, not higher dimension, but try to construct an extension with infinite dimension? It's possible to do that? For
Infinite
example,
dimension.
you have infinite dimension, right?
Well, for that, first
yes,
you have
maybe
to define.
A question out of the idea of the presentation, but I don't know if you have a think about the possibility of include infinite dimension of the problem with solutions.
Right, but I mean, for that you first have to define quantum field theory on infinite dimensions. I mean, use
Yes.
homogeneous theories. Then maybe you can define inhomogeneous theories later.
Mm-hmm.
Right. So, but I don't know what the quantum field theory on infinite dimensions. So.
Okay. Well, maybe I saw that about it by, I don't know, studying the same, but with some type of operator with other type of property. Maybe I am not sure. I'm just an idea that I have when you mentioned the last part. Well, thank you for your answers.
Okay.
Is there any other question?
Can I ask a question?
Yes.
Could you give some comments about the perturbation of position-dependent parameters? Can you consider such perturbation?
So you consider this position-dependent term as a perturbation?
Yes, that parameters. Because you have mentioned that in experiment you can consider the heterogeneous systems joined by together.
Right.
Then in experiment you can control that one part. That means we should consider some perturbation or some control of the position-dependent parameters. So I am wondering, it is possible or not to consider theoretically that situation.
Well, classically, I mean, this is always possible, but I mean,
I'm asking about the classical perturbation, of course.
I mean, you can, as I said, you can consider that inhomogeneity as an external field or impurities or something like that. Not only perturbation, you can,
So I'm asking what is the effect of that change of the external parameters?
Right.
Could you give some comments about that effect?
So if you change the position dependent function, then we will obtain some different field configurations, fields of solutions. But if the asymptotic values are the same, then that will not change the energy. Only the profile of the solution will change. As far as the supersymmetric solutions are concerned.
Thank you.
Okay. Is there any other question? If not, let's thank the speaker again for a very nice talk.
Thank you.
Thank you.